Okay, so we'll look at the main principles of transactions. We're looking at how concurrency control can be achieved. We'll do an overview of transaction commit, which is an important protocol that's needed for implementing transactions. And then we'll look at extended transactions. So the idea of transactions is that they're used to control operations on persistent, long-lived, disk-based shared information. So any kind of data that you want to manipulate, and you want to make sure that that data doesn't change in an inconsistent way. Mainly because you're worried about concurrent access to that data. So in distributed applications, you've got a server, you've got data on it, you want the world to access that data in some kind of format, whether it be a web page or you're just sharing data between different applications. There's usually going to be multiple requests happening at the same time, and so you want to be able to control access to that data. And that's the main idea behind transactions. Transactions is a method of control and access to the data to make sure that it's always consistent and always adheres to whatever consistency rules you apply to your particular application. It applies to files, to databases, and to even objects in object-oriented applications. So the main aim is to ensure a consistent outcome of related operations on shared information, whatever that information might be. Operations or remote objects are invoked through the use of remote procedure calls or messages or whatever middleware techniques we want to use, and transactions ensure that only consistent state changes to objects take place despite concurrent access and despite any failures. If a failure has happened, you need to be able to take the system back to some kind of state which you consider to be consistent. Okay, so for example, the simplest example is a bank transfer. If I transfer some money from my bank account to another bank account, and during this operation the second bank account goes down, then we shouldn't be in a state where nobody has the money. Okay, the money needs to reappear somewhere. So we need to be able to recover from that somehow. So the idea is that all intended changes to objects take place or none take place at all. So we need to be able to have several operations or run several operations, and either all of them completed or none of them completed. So this is called the atomic property of transactions. Let's say you want to transfer money from one bank account to another. So this should be atomic. So without a transaction, a failure at this point here could mean that current is debited but savings is not credited. So you're trying to debit the current account and credit the savings account. Some kind of failure happens in the middle, and you end up the system being inconsistent because you've removed money from one account and the other account doesn't receive the money. So you end up with zero money in both accounts. So what we want to do is to place these two operations into the context of a transaction. Through Java, for example, is that you simply use annotations. So you'd specify, you'd say these are the operations that are going to be part of the transaction, and something called a transaction manager in the background takes that into account, and it starts to do everything that needs to be done to be able to recover from problems like failures or one of the operations not working for some reason, and so that it can recover to the original state the system was in the first instance. So what you want to do is to do something like this. Say we're starting a transaction here and the transaction will end here, and all the operations in the between, we want to execute these as part of a transaction. So transactions have properties: atomicity, consistency, isolation, and durability. Atomicity means that transactions are either performed completely or no modification is done. So this is the idea that either every single operation within the transaction executes as it should completely. If either one of those operations fails, it's as if none of those tasks have run. Even if 9 out of 10 of them have completed, we need to be able to roll back those 9 back to their original state as if those 9 weren't completed. So the start of a transaction is a continuation point to which we can roll back to, and the end of the transaction is the next continuation point. So the system can never be anywhere in between those points. It has to be either at the start of the transaction or at the end of the transaction. So the second property of transactions is consistency, which means that shared resources should always be consistent, and this is application defined. It's up to you to decide what it means to be for a system to be consistent. So as a simple example of a snacks machine, for example, You should say a consistency property for a snacks machine could be something like the total amount of money plus the total worth of the snacks within the machine should be £1,000, for example. So if it's less, then something's gone wrong. So maybe one of the snacks has dropped and somebody's taken it without paying for it, for example. So you need to be able to check that and test that. And whenever you run the transaction from start to finish, at those continuation points at the start and the end, you want to do tests to make sure that it is in a consistent state. So a transaction takes a system from one application-defined consistent state to another application-defined consistent state. So it's completely application-defined. It depends on your application and what it means for you for that application to be consistent. So the other properties are isolation and durability. So isolation is a way to achieve the last two properties, or essentially to achieve this property of consistency here. So the one way in which we want to achieve consistency is isolation. So each transaction executes without interference from other concurrent transactions, and that's something that we need to guard against. So as we said previously, you have a database system, and there's going to be multiple attempts to access that database. So we need to be able to isolate those transactions from each other and make sure that they each access the system independent from each other, so that we don't break the consistency property. So modifications in a transaction should not become visible to other transactions before it finishes. So whenever there's concurrent access to a system, it's not real concurrency. Okay, we need to be able to manage those accesses so that they're actually sequential, they're not concurrent. So you only allow concurrent access if there's no modification happening, like if there's only a read. But if several transactions are trying to change or write to the data within the system, then we need to isolate those and run them independent from each other. So basically, you can't have consistency without your isolation, and require the use of concurrency controls such as two-phase locking. So we'll look at what two-phase locking means in a little bit. So another property that's necessary to achieve transactions is something called durability. So this idea that you go from one consistent state to another consistent state can't happen if you are not able to durably store the data or the state of the system in some kind of persistent storage. So therefore, durability is a very important concept. So after successful completion of a transaction, all state changes to objects are on permanent storage that survives any kind of crashes or whatever. So one of the things that we use to enable transactions is something called the transaction commit protocol. It's used during the termination of a transaction to ensure that either all object updates within the transactions have their new states recorded on stable storage, or if the transaction aborts, then no updates are recorded. So it's the way that the transaction manager manages all the various objects and the various operations on accessing the object. So you can't have one phase for this protocol. So if you had it in one phase, a single phase commit protocol basically tells all objects to commit once the transaction is completed. So if I as a transaction manager think that everybody's completed, and I send a commit command, then one of the problems that could happen during the time that the objects are committing, meaning they're storing their results into permanent storage, one of the problems that could happen is that one of them could crash. Okay, and if one of them crashes, that means all those changes are lost. So we haven't achieved a perfect transaction. We have 8 out of 10 or 9 out of 10 of the operations have completed, but one of them has crashed for some reason. So what we need is usually two phases for a commit protocol, and it's usually something called a voting phase and then the commit phase. So in the voting phase, you tell everybody, are you ready to? So I'm going to tell you to commit in a little bit. So are you ready to commit? So what the various objects do then, if they've completed, they say yes, we're ready to commit, and also they store their state into permanent storage, so that if they do crash later on, they can bring up the new state, whatever it was when they reinitialized. So typical failures causing a transaction to be aborted include node crashes, network partitions, so message losses because of network partitions, etc. Usually there's a begin command which tells the transaction manager that we're going to start a new transaction. And then the other possible commands are either commit, so if the transaction manager thinks that everybody's completed correctly, then sends a commit command, which indicates the end of the transaction. It persists state changes to stable storage and makes changes accessible to the next transactions coming on. Or if the transaction manager notices there's a problem with the overall transaction and we need to abort, then it just tells everybody to abort. So it's the end of the transaction. It tells all the objects, the participating objects, to roll back because the transactions failed for some reason. So those are the basic phases, the possible phases of a transaction. So there are various types of transactions that you can have, the most basic of which is something called a flat transaction. So that's a very basic transaction. There's no layers to it. It's just a single transaction with multiple tasks to it. And one transaction follows the other. Okay, so there's no nesting happening. So a new transaction only begins if a previous transaction has either committed or aborted. So it's as simple as that. So aborting of a flat transaction leads to loss of all work associated with the transaction. So we need to, even if it's taken a bit of time, it doesn't matter. We just throw all that work away and we reinitialize the initial state. So abort can happen either explicitly or implicitly. Explicitly means that the coordinator or the transaction manager tells everybody to abort. Or implicitly, if any of the participants fails, then that basically sends a message. The transaction manager will notice and will tell everybody to abort, but it's considered to be implicit because it's happened due to a failure, not because of some kind of logical decision. Or you can have a successful commit, and the system continues to a new state. So these are the definitions of them. That's what a successful commit is, and abort means that the system is rolled back to the state it was before the transaction. So this is what a flat transaction looks like. So you start the transaction, a transaction completes, and you commit. You can start another transaction, and the transaction manager sends an abort command, and so all the objects participating in the transaction have to roll back their state to the initial state. Or a failure happens, a crash happens, so that's the implicit abort, in which case everybody rolls back. The other type, and other types of transactions you can have, so one thing that you can do is that you can nest your transactions. And this is useful, for example, where you have a lot of transactions, for example, all doing the same thing, and you don't want the whole system to abort if you just put them within a single transaction. An example of that would be, let's say, a bank decides to apply an interest increase to one of the accounts that all of its customers hold. So it runs the algorithm, and the algorithm automatically goes to each of the accounts and applies the interest increase so that everybody gets their extra money, whatever it is. So each one of those, each of the bank account interest increases will be a transaction, but you also want to place them all within an overall transaction. In that case, if one of them fails, it doesn't matter. It shouldn't affect the other bank account. So if my bank account interest increase fails for some reason, let's say at the moment when they apply the algorithm, I try to access my bank account. So in which case, it won't be allowed to happen because you can't have two accessing at the same time, two doing writes at the same time. So in which case, my interest increase would fail at that particular moment, but that shouldn't affect your bank account. It shouldn't affect the interest increase in your bank account. So your transaction will complete, and so will everybody else's. So that operation would place it within a nested transaction. There's an overall transaction which defines what the algorithm is, and then all the operations within the nested transaction operate as separate transactions. So in a nested transaction, we call these child transactions, are embedded inside a parent transaction. So it's used to set continuation points during the parent transaction. So parts of the complex transaction can be done without losing all changes. So commit or abort children independent of parent. So any of the children, like my bank account, can fail, and it shouldn't affect the overall parent transaction or any of the other children transaction. So a child abort only changes in the child's are rolled back, and a child commit means that the changes are visible to the parent and to subsequent siblings. If a parent aborts, then everybody aborts. All the children transactions abort. So, for example, the bank notices for some reason that the algorithm is incorrect. So they say abort, we need to reapply the algorithm, so everything goes back to its initial state. So this is what a nested transaction might look like. So I start a parent transaction, and then within that, I have several children transactions. And the first two have completed successfully, but the third one here has had to abort. It's had to roll back to its initial state for whatever reason. And then at the end you commit, and you notice, for example, that 10% of the children transactions didn't succeed, so then you reapply that algorithm just to those, and then the second time round or the third time rounds, hopefully it'll complete when access to those accounts is possible. Yeah, so that's called a top level transaction, and all the others are your children transactions. So so to support transactions, we need to have, as we said earlier, the recoverability property. So in order to do transactions, then objects need to be made recoverable. So that's a very important aspect of transactions. Without recoverability, then it's just not possible. So a recoverable object must be capable of taking part in the commit protocol, which I touched upon a little bit earlier. So what happens is that a recoverable object, when it decides it's going to take part of a transaction, it basically becomes a transaction object, and it needs to maintain two states. So it needs to maintain both its original state S, and then it needs to record the modified state of S also on stable storage. So at the end of the commit protocol, the object state is either the modified S if the overall transaction is successful, or if they have to abort for some reason, then you go back to the original state of the system. Looking more deeply at concurrency control, and the property of isolation that we talked about, operations or transactions need to be shown to be serializable. So serializable means that they follow one after the other. So if you have multiple operations that appear to happen at the same time, if you want them to operate as part of transactions, in fact what happens is that they need to be serializable, which means that they don't happen at the same time, they happen one after the other. So non-serializable executions can, as we said, can result in consistency problems. There's an example of this on the next slide. So here is a very basic example that's used to describe the serialization problem. I've got a customer here standing at an ATM machine, and what they want to do is they want to withdraw some money from the account, and you've got a clerk at the account and they want to credit the account with a certain amount of money. So in this example, the customer wants to debit the account £50 and the clerk wants to credit the account £50. And if you don't run this as part of a transaction, then this is what could happen. So this is the overall balance here. So here you've got, at the customer side, let's say you've got some kind of a variable. When they withdraw their money, it stores the new amount, which is £50. And also the clerk accessing the account at the same time, adding money to the account, the same thing happens. So the new amount variable adds 75 to 50, and then the global variable balance becomes equal to new here, which sets the overall balance to 25. And the clerk here at the same time, or very close to that, sets the balance is equal to new, which sets the amount of money to £125. So you end up with a total amount of money here of £125 if you don't run this using transactions. Yeah, so it should be £75. Here the customer was lucky in that the clerk's operation happened after their own operation, so they ended up with extra money in their bank account. But if it happened in reverse, if the clerk had been accessing the account before the customer, then they would have ended up with £25 in their bank account. So what we want to do is, so this is the kind of error. So when they were first building systems like these errors were happening all the time. So that's when they realized, okay, we need to do something about this. We can't allow concurrent access to the same variables. We need to have transactions. So this is called the lost update example. So there's some data somewhere is being lost because you have concurrent access to the account. So the data is in an inconsistent state and we're losing information and it's incorrect basically. So a non-serial schedule loses update performed by the customer. A serial schedule on the other hand should result in a balance of 75, so that's what the correct value should be after the debit and the credit operations have been performed. So what we should do, either the counter credit operation must update the balance before the debit calculation or vice versa. So we shouldn't be doing them at the same time. We should be doing them one after the other. Okay, so this is what we should be doing. So the customer here wants to debit their bank account £50, and at the moment that they decide to do that, what we do something is called resource locking. And then the clerk here, when they try to credit the account £50, they're not allowed to do that. The system should block them, basically. And the customer carries on, so the new variable is 75 minus 50, the balance is equal to new, it's set here to 25, and then now that the transaction is completed, you unlock the resource, okay? And then the clerk can continue. So here, when they're blocked, they might have received an error, come back and try later, or if it's something that the system knows it's going to happen very quickly, it might say do a countdown and refresh the page in a few seconds and allow them to continue. So there are different techniques to block and unblock, but the main thing is to actually block and unblock the resource. So once they're unblocked, then the clerk can credit the account. Also, when the clerk accesses the account, obviously it's locked as well, so nobody else can access it while this operation is being performed. So the new balance is set and the overall state is set. So now we've got a correct amount of money within the bank account at the end. And then once the clerk is completed, then the resource is unlocked. So now that this brings us this brings us to the idea of locking. So how are resources locked within transactions? And one of the most widely or most commonly used methods of locking resources is a protocol called two-phase locking. It's a protocol that has two phases to it, as the name suggests. So processes acquire locks before access to shared resources and release locks afterwards. So these are the two phases. So we've got the growing phase and we've got the shrinking phase. So the growing phase, a transaction acquires locks and does not release held ones. So during the growing phase, let's say you need 20 resources to complete your transaction, then you lock all of those 20 resources and you don't release any of them until all the operations on all the resources have completed. So that's the growing phase. You hold locks on all of them, and then you've got something called the shrinking phase, where once you've completed whatever you need to do with all these resources, then only then are the resources released. So in shrinking phase, locks are released and no new locks are acquired. So here it says at the end, all held locks are released together to ensure that a port does not affect any other transaction. So in the growing phase, so here you've got several resources and you lock all of them, and you don't release any of them until you've completed whatever you need to do with each and every one of them. So even though I've completed access to this first resource here, once I get to this resource, something wrong might happen. So I might need to go back to this resource at some point and roll it back to its initial state because the overall transaction has failed for some reason. So she should always hold the locks on all of the resources until all of the entire transaction is completed successfully. And obviously this is very difficult. Let's say you release the lock on this particular resource and then you realize I need to roll it back, but some of the transactions held a lock on it, then it could be a disaster then, because you can't go back to that resource because it's locked. And even if you go back to it after that lock's been released, it's in a very inconsistent state then, because the second transaction has modified it, and then you have to go back to that second transaction and tell it you have to go back, so it becomes very, very messy. So that's why in the growing phase, you hold all the locks and you don't release any of them until the entire transaction is completed. So in order to do locking, we have something called a lock compatibility matrix. So what we have are things called read locks and we have write locks. And this is all part of something called a lock policy defined by a lock compatibility matrix, as I said. And the policy is usually to allow concurrent reads but exclusive writes. So this is how it would be implemented using this principle. So when you apply the lock, you would apply a write lock here, and then you would unlock the write lock, and the same thing applies for for the bank clerk, they apply and then unblock, they lock and unlock the right lock. So this is fine if you have a small number of resources, okay, but in normal databases and servers, usually what happens is that you're possibly trying to access thousands of resources at the same time. So we need something slightly more complex than that. So something comes into account called lock granularity. And the idea is that two-phase locking is applicable to resources of any granularity, but it's inefficient if transactions involve a large number of locks or objects that you're trying to lock. Okay, so let's say you've got a database and you want to access, as part of your transaction, 1,000 files within a folder. Then there are two ways you can do that. You can either lock the folder, okay, which would give you access to the entire folder, and you can change it and modify it. But so you're locking everything within that folder. There might be 1,000 files in there you want, but there might be 10,000 files that you don't want. So that reduces concurrency. So you're basically restricting access to the folder to other transactions or other users that are trying to access that folder to do whatever they want to do with it. The alternative to that is that you go into the folder and you lock all the individual files that you need. And the problem with that is the locking overhead, okay? Because each lock takes a little bit of resources from the system. So if you're doing 1,000 locks, then that's a huge amount of resources, a huge amount of work that the transaction manager is doing, and it's going to slow down the performance. It's going to affect the performance of your system. So we say that there's a trade-off between the degree of concurrency that you can have and the locking overhead. So it's a balance, a difficult balance to achieve. Do you want high concurrency, in which case you need to lock all the resources, but the problem with that, you reduce the performance of the system because you are locking so many resources. Or is performance more important, in which case you lock the overall folder, but then there's no concurrency because nobody else can access the folder. So there's a trade-off between the degree of concurrency and the locking overhead. To try and solve this problem is something called hierarchical locking. So it doesn't solve the problem completely, but it attempts to help a little bit. And it is very effective. You can lock composite resources, like we said. So you can lock a resource or its parent folder, or its composite object, whatever you want to call it. So examples of that: files and directories, which contain other directories, containers or collections of objects. So this applies to any kind of system where you have files containing other files, containing files, containing whatever, or data structures containing objects. So this is where hierarchical locking can apply. And another example here is going back to a bank account example. So the bank will have an overall headquarters somewhere in the country. They might have groups of branches, so these could be cities. So there could be a group in Newcastle, a group in London, a group in Leeds, for example. So in Newcastle, I don't know, there are probably 20 banks for Lloyds all over the city. And then each bank will hold an account for individual customers. So this is, and banks do a lot of operations on their accounts. They do various things, like we said earlier, doing interests increases or reductions, or doing various operations on them. So they need to lock their resources and unlock them for various types of operations all the time. In order to alleviate the problem we mentioned earlier with hierarchical locking, is that we've invented something called an intention lock. So we lock all component objects by locking the composite object that contains them, but instead of acquiring within the folder, you don't acquire a read or write lock. Instead of applying a read or write lock to those, you apply something called an intention read or an intention to write lock. And what you're doing, and when you do that, essentially what you're saying is you're telling the outside world that you intend, for example, to write to some of the resources within the composite. Okay, so you apply an intention to write on the bank, and that means that you're going to go in and you're going to write to some of the resources, some of the accounts within the bank. And by applying the intention to write on the composite, what you're doing is you're preventing anybody else from coming in and applying a write to the bank account. So you're free to do write locks, unlock some resources within the composite, and nobody else can come in and disrupt your operation by doing a complete write lock on the overall composite. So it reduces the overhead on locks. It's beneficial because you allow people to come into the composite and do their own operations as you're accessing certain operations. as you're accessing certain objects. But that does increase the complexity of our compatibility matrix slightly. So this is the compatibility matrix for hierarchical locking. For the one for reads and writes only, it was very simple. So you just had read and writes. For this one, we have intention to read and intentions to write. So you notice that whenever I apply an intention to read, then anybody else is allowed to come in and do an intention to read, a read, or intention to write, but nobody's allowed to apply a write lock, for example. And a read is compatible with intention to read and read, but not compatible with those two, and so on. Yeah, so an intention to read on composite resource indicates a transaction has acquired or is about to acquire a read lock on object within the composite. And it prevents somebody coming in here and applying a write lock on the composite. But they're allowed to come in and do another intention to read or an intention to write, for example. So here's an example of where you would use such a lock compatibility matrix. So you've got a bank, contains G1, contains B1, contains a number of accounts. So we'll go back to our picture of the bank. So you've got your bank here, it has the groups. So one of the groups is G1, and G1 has got a branch called B1, and branch B1 has a number of accounts. And we've got a number of transactions, and what we want to see if these transactions are compatible with each other or not. Should the system allow these transactions to happen concurrently or not? So transaction 1 sums the balances of a customer's account at B1. So it sums the balances of a customer's account on B1. So it assumes that a customer has multiple accounts. So it might be a savings account plus another savings account plus an investment account plus just a current account. And all this transaction is trying to do is look at that customer's accounts and add how much money do they have overall. And the accounts of the customer are within branch number 1. You've got a second transaction here, which transfers funds between two accounts within branch 1. So it doesn't say anything about whether or not the two accounts belong to the same customer, or if it's the same customer we're referring to within transaction number 1. Transaction 3 sums the balances of all accounts at group 1. So the easiest way to solve such a problem is just to put your transactions at the top here. So I've got T1, T2, and T3, and so let's look at them one by one. Okay, so I'm just going to put a line top to bottom here. So what does transaction 1 say? It says sum the balances of a customer's account at B1. So if I want to sum all the balances within B1, intention to read. At the group level, it's also intention to read. At the branch level, it's also an intention to read. And at the accounts that you want to sum the balances of, so those will be individually reads. Okay, so that's transaction number 1. So transaction 2 transfers funds between two accounts in B1. So you have to lock the accounts in a right sense, because you don't want anybody else, as you run the transaction, you don't want anybody to be able to access it at the same time, because there's writing going on. So this is an intention to write, an intention to write, an intention to write, and here you're going to write to some of the objects in there. Okay, and then in transaction 3, so first let's check that we've done it correctly. So transaction 2, intention to write lock on bank, G1 and B1, and write locks on the two account objects. So T3 sums the balances of all accounts in G1. So here, so I'm summing, so again, it's an intention to read here. And because I'm going to sum all the balances in here, I'm just going to access every single resource in there. Then now it's okay to acquire a read on the entire composite resource, because there is no resource in there which I'm not going to access. And it's what I'm going to perform the operation on. So we acquire intention to read on bank and read on G1. So let's check I've done that correctly. So T3 must acquire intention to read lock on bank and read lock on G1. So, and the question is, are these transactions compatible with each other? So what we do is we look at our lock compatibility matrix here on the right hand side, and let's compare T1 and T2 first of all. So IR and IW are compatible, so that's fine. IR, IW, so these are all fine. And read and write are not compatible with each other. Okay, so this here, accessing these resources at the end here, is not compatible. So therefore you can't have T1 and T2 running at the same time. So these must be done sequentially. T1 and T2 only if the accounts are disjoint, which means that only if the accounts that we're accessing are different from each other. Okay, but in general, they shouldn't be run at the same time, but they can be run at the same time if you know that the accounts that you're reading from and you're writing from are not going to be the same account. So here it's saying you're summing the balances of a customer's accounts at B1, and here you're saying T2 is transferring funds between two accounts. So if the accounts referred to in T1 are not the same accounts referred to in the accounts in T2, then yes, you can run those two transactions at the same time. But generally, if you don't know, then those two can't be run at the same time. So T1 and T3, so you've got an intention to read and intention to read, which are compatible with each other. Intention to read and a read are also compatible with each other. So transaction T1 and T3 is fine. So T2 and T3, so intention to write and an intention to read are compatible with each other, and an intention to write and a read are not compatible with each other, so that's a no. So you can't run, so T2 and T3, so this pen's terrible, and T3 are not compatible with each other. So as we said earlier on, that when resources are committed, when a transaction is said to be complete, we use something called the two-phase commit protocol. So here's an example where you've got a client here and you've got a number of servers, and the client sends a commit message to servers but crashes halfway. So here we're assuming that the client is actually the transaction manager. So they're sending commit messages to this guy, this guy, this guy, but then they crash and they can't, the client themselves crashes, and these messages here never get to their destination. So a problem then happens is that if we're using a single commit protocol, then you can't guarantee transaction behavior because the client is crashed, haven't stored their state into stable storage, and also these guys here might have committed and they might have not have stored their initial state to stable storage. So that's why we need two phases for the commit protocol. So rather than just sending the commit message as it is on its own, then we have an additional phase, as I said earlier, called a voting phase. So first, before you ask to commit, the transaction coordinator asks every participant to vote on whether to abort or commit. If they vote to commit, then you must persist the state of each object that votes to commit has to persist their state into temporary storage. Just in case they crash, they can reload their state, or in case the transaction coordinator crashes, they are able to reload their state from storage. So that's the first phase, it's the voting phase. And then you have the second phase called the commit phase. If all participants vote to commit, the coordinator sends a transaction commit message to all participants. If any voted to abort or failed to vote, then must send a transaction abort message to all participants. So only if they all vote to commit does the coordinator tell everybody to commit. Within distributed computing is the idea of component-based middleware. So what we have within component-based middleware, we have separate services for persistence, for concurrency control. We have databases that support their own ACID transactions. So most databases do support ACID transactions. Whenever you try to access a database and you try to write to a field within a database, the database will automatically lock the database so that nobody else can access it at the same time and trying to write to that same field. They don't allow concurrent access. They don't allow an inconsistent state to happen within the database itself. What we're trying to do here is to apply what databases do within distributed computing generally, within objects that you're trying to access and data that you want to manipulate. So we have all these services. We have services for persistence, concurrency control, databases that are transactional. So what we need is some kind of a service within the middleware to do transactions on objects. So we need to do both of these things. So we need to do A and B. So objects need to be able to become transaction aware, so that if to participate in this two-phase commit protocol, they need to be able to store themselves automatically into stable storage, so that they can recover if they need to. And we also need to use middleware to provide the co-coordination mechanism for the commit protocol. So you need to have the middleware acting as the transactional coordinator. So you end up with something that looks like this. So you've got a coordinator here on the right-hand side, and if you have several transactions happening, or several operations that are happening that you want to be part of some kind of a transaction, then you can register those, any resources that you need and any operations that you need with this coordinator on the right-hand side. For example, if you're using component-based middleware of J2EE, is that there's a command called begin, which starts the coordinator here on the right-hand side, and then all the operations, for example, debit and credit, which are initiated on these resources here. So those resources would automatically be registered with the coordinator because they're placed within the context of a transaction. And whenever the operations of debit or credit are complete, then a message is sent by the coordinator. It's sent either by the coordinator or it's sent by whoever's last in the transaction. So a commit message is sent to coordinator, and then the coordinator initiates the protocol. So this is the voting phase. So they tell each of the resources to prepare themselves and vote on whether or not you can commit or not. And if they vote yes, then the coordinator sends the commit message in the second phase. So there's always two phases: there's the voting phase and the commit phase. So those are the basic principles of transactions. So they have the asset properties. And the main idea is that we want to be able to run several operations as if there was a single operation within this thing called a transaction. And we also want to be able to separate transactions from each other so that you don't have inconsistent access to various resources. And you just need to be able to know basically the relevant libraries to use and what annotations to use, as you would with any other service within component-based middleware. So you become familiar with them, and then it becomes easy to use them. So in the past, these things would have had to have been manually coded very carefully. Nowadays, there is a lot of support to use them. So there's another type of transaction. It's called extended transactions. So the transactions that I've been talking about earlier refer to operations and that are batched together into transactions that are meant to run very, very quickly. So they're meant to be running within seconds or minutes at the maximum, but they're usually very, very quick. So you can have them within the context of a transaction. There are other types of applications where you have several operations running in a long-lived manner. So they're not short-lived like the examples I gave earlier on. So an example of that is a booking. If you're booking something for somebody, and as part of the operation, the customer has to actually go ahead and do their traveling and go to a hotel and go to a restaurant, and so the entire booking process has several operations which, in order to run, they're taking weeks or months. Then in that context, it doesn't make sense to run a transaction because you can't lock a resource for such a long amount of time. So there are some resources which you just can't lock them because nobody else can use them for a week or a month. So you can't run applications within those types of applications. You can't run them within the context of traditional transactions. So what we have, instead of if you want some kind of consistency and recoverability when operations fail in those contexts, when things don't happen as you want them to happen, then we need to invent something new. So traditional transactions don't work, so they invented this thing called extended transactions. And the way they work is, instead of rolling back work, because you can't roll back work that's such long-lived, you can't roll back somebody traveling to another city and finding out, for example, that the hotel is overbooked. So you can't roll back that operation. It's impossible. So what you do is, so the way they solve that problem is by having compensation transactions. So instead of rolling back, you add another transaction onto the end of the operation, and you say, instead of going to this hotel, for example, you go to this hotel, or if your taxi hasn't arrived, then instead of this taxi transaction, then you add another taxi transaction, or you add a bus transaction instead. So you instead of rolling back what you're doing, you're adding things on, called compensations. So the traditional transactions are what we call asset transactions. They're a sound foundation for building high integrity business applications that are meant to be short-lived. So these are what we call short-lived applications. They preserve consistency of application state despite concurrent access and despite failures. So they're very good for those types of applications, but they're less well suited for long-lived applications that are running for hours or days. So you need something new for that. Long-lived level transactions can be problematic because they reduce concurrency in the system. If aborted, you'll end up rolling back a lot of valuable work, so it's just not practical to do that. So you can't place them within nested transactions because aborting just one of the child transactions might not be acceptable, and might not even be possible. So instead of having asset transactions, what we have non-ACID and extended transactions, where instead of having all or nothing, we introduce something called all or something. Okay, so it's a more relaxed view of transactions. You hope everything will be achieved, but if not everything is not achieved, you don't roll back to the initial state. You allow some of the things that have been executed to continue to be executed, and you try and move forward. So this is a simple example. So here we have a long-running business activity. You've got a number of transactions. So you've got booking a taxi, followed by reserve a table at a restaurant, reserving a seat at the theatre, and then booking a hotel and a room, and so on. So here we've got a sort of a view on that. So this is an example of how this could be structured. So you've got transaction 1, and then transaction 2, and transaction 3. In this case, for example, they're meant to be running in parallel, and then booking the hotel and the room, and then there might be some other transactions after that. So if these run as expected and everything's fine, there's no problem. But if some transaction aborts, then we need one or more compensation transactions rather than aborting the entire activity. It doesn't make sense to abort the entire activity. So you do something like this. So let's say T4 here aborts. So as a result, you might need to undo some changes prior to T4. So if T4 is not possible, then you might put them into another hotel, or cancel some other activities. And they, for example, book cinema tickets and another hotel. So it's that idea. It's that idea of instead of rolling back things that have already done, you replace things that can't be done with other things that you're able to do later on. So that's the basic idea of extended transactions.